Good evening, everyone. Today we'll discuss first the reaction kinetics, the rate of the reaction, and as well as the reversible reaction. And later in the session, I will discuss the doubts related to January 2018, Unit 1. So, rate of the reaction or speed of the reaction, it is similar to that what you have studied in O levels. The only addition will be there. You will study an extra Maxwell-Boltzmann distribution graph which shows how the energy is distributed between the particle, and using a Maxwell distribution graph you should be able to say what happened to speed or the rate of the reaction and how the graph will change. First, starting with the basic concept, the collision theory. What is the collision theory? It simply states that as the number of the collision increases, the rate of the reaction will also increase. And effective collision, when the particles have sufficient energy, the minimum possible energy for the particle to collide and start a reaction, that's called activation energy. Example, this is energy profile diagram for exothermic reactions where reactants have more energy and the product is having less energy. Say reactants have 30 joules of energy, but then they don't have sufficient amount of energy to react. So what they do, they absorb the energy. When they have the 70 joules of energy, they start up the reaction. So minimum possible energy which they required for reaction to start. Reactants were already having 30 and we supplied or the particle taken 40 joules to reach the activation energy, and once they reach activation energy, they will form a product. As you can see, the energy which is taken in is small proportion as compared to energy which is released. So overall reaction will be an exothermic reaction. And the minimum possible energy at which it start, reaction start, we call that as activation energy. So even there are collisions between or among the particles of reactant, but they are not forming a product. So these are the collision but not effective collision. So a collision which leads to a product, which result in a formation of a product, that collision is known as effective collision. This is a Maxwell-Boltzmann distribution graph. You should understand each label. Basically what happened, how to simplify this Maxwell-Boltzmann distribution graph or how to show this. This is actually showing the distribution of energy among the particles of reactant. On x-axis we have number of the particle and on y-axis we have energy. And on x-axis we have number of the particles. To understand this graph, you can simply take like example of one class. If you take example of a class, say there are 10 students in the class. Now what you are doing, you are comparing the height of the 10 students. What you will find when you are comparing the height of the 10 students, you will find some of them are short, some of them are very tall, but most of them have average height, like this, approximately same height. There are short students as well, there are tall students, but most of them have average height. Same thing happened for the particle or distribution of energy among the particle, that some of the particles have low energy, some of the particles have high energy, but most of the particles will have average energy. So this peak, what this peak represent? This peak represent, or if I change the label, instead of number, because it can be number of the particle. If I took the number of the particle and energy on y-axis and number of particle on x-axis, or other way around, so this was number of the particles, and here on x-axis I have energy. So when we compare the distribution of energy among the particles. So this is a distribution. What it shows, what this graph shows, it shows that some of the particles will have low energy, some of the particles will have high energy, but most of the particles will have average energy. So there are particles with low energy, there are particles with high energy, but most of the particles will have average energy. So when we represent this graph, it will be always an identical shape of the graph. As you can see here, you have to understand the labels as well. The Maxwell distribution of Maxwell-Boltzmann energy distribution, which shows how the energy is spread out among the molecules of gas and liquid at a particular temperature. So this is a graph. As you can see, this is not the maximum energy. This means most of the particle will have average energy. So region below this or before this, that shows few molecules will have low energy because collision caused some of the particle to slow down or lose their energy. Most of the particle will have a probable energy, not this. It does not mean that the mean energy or average energy, probable energy, because that is not the mean. Some of the particle will have low, some as high, but when we take the mean, this is not the mean energy, this is the probable energy that most of them will have energy in this range. An area under this graph, what it represents total number of the particle present. When we find the total area of this graph, that will give us how many particles are there. And most of the molecule will have energy between the two extremes, but distribution is not symmetrical. As you can clearly see, this region, the probable energy, the particles which have energy less than probable, smaller area is there, but the energy, the particle which have energy more than the probable, that's large area. So means most of the particle will have energy more than the probable energy. Then there is a minimum possible energy at which the reaction start. So the energy at which this reaction will start, that is called activation energy. So the region, the particle after this activation energy are likely to react and form a product. So the shape of the graph will change as the temperature changes or as we uh, change the concentration. So what is the effect of temperature? Like this is a normal distribution of Maxwell-Boltzmann. Is it clear to everyone? The distribution, the Maxwell-Boltzmann distribution of energy among the particle. Some particles will have less than the probable energy, some have more than the probable, but most of them have a probable energy. Is it clear? Now what will happen, how the graph will change as we change the temperature. So you can clearly see when we increase the temperature, the mean energy or the average energy shifted, because what it shows that the most of the particle will have higher energy. So when we increase the temperature, the height of the peak will decrease and it will shift towards right hand side. The area of the two graphs will be same. Why the area of the two graphs is same? Because they have this area of the graph represent the total number of the particles, so number of the particle remains same. That is why area of the two graphs is unchanged. But the first graph is having a higher peak, so less base area. The second one is having a smaller height, so it will have a larger base area. But the total area of the two graphs is same. So variation of temperature, how the graph will change. As you can see, this one is at lower temperature, but when we increase the temperature, the peak is shifted towards right, the height of the peak will decrease. And that is also a reason why increase in temperature increase the rate of the reaction. You can clearly see that when the temperature is low, few particles will have energy more than activation. But as we increase the temperature, this area increases, like this total area. So that increase, when you increase the temperature, so greater number of particles will have energy more than activation energy. That is why the rate of this reaction will increase as greater proportion of the particle have energy more than activation. So the probable energy and the mean energy both are shifted towards right as we increase the temperature. And if I say this is a point where the reaction start. So at 25 degree, you can see only the region which is under the graph, that is the region which is under the graph. So few particles will react and form a product. As we increase the temperature, activation energy remains same, but the peak shifted towards right. So you can see greater proportion or greater number of the particles have energy more than activation energy, which result in greater number of collision. Effective collision leads to faster rate of the reaction. How we can find the speed or the rate of the reaction? What we can do, if we can sketch a graph for concentration and time, it can be both ways. It can be concentration or amount of the change in the mass, or for the reactant, or volume of the product. When we plot a graph for mass on y-axis and the time on x-axis, in the beginning we have the greater mass. With the passage of the time, the mass start to decrease and until it will be no change in mass. So when the mass is not changing, it means the reaction stop. How we can find the rate or the speed of this reaction? By drawing a tangent and finding the gradient of this tangent, we can find the rate of the reaction. Here the tangent is steeper, so the reaction is fast. Here the reaction is getting slower, and when it is exactly horizontal, the reaction stops. You can also sketch a graph, plot a graph for volume of the product and time. On y-axis we have volume of the product, and x-axis we have time. In the beginning there is no product, but with the passage of the time, amount of product increase, but the rate at which the product is forming, that is decreasing, because the amount of the reactant particle is decreasing. To find the rate of this reaction, what we can do, we can draw a tangent. In the beginning the tangent is steeper, so the reaction will be faster. Here the reaction is slower, and eventually the reaction stops. There is no reaction because there is no change in concentration. Now, what is the effect of increasing the concentration or increasing a pressure? Basically, when we increase the pressure, we decrease the volume. This is for gases. And when we decrease the volume, it means we increase the concentration. Like you have two containers having a same number of the particles of the reactant. But what you did, you apply a pressure. So this is the original volume. Now what we did, we apply a force on unit area, create a pressure. So as we create a pressure, the particles will come closer to each other. As the particles come closer to each other, the volume decrease. It means the concentration will increase. So higher concentration, when we plot the graph, higher concentration and lower concentration, how the shape of the graph will change. So you can see at a lower concentration, less area; at a higher concentration, more area, greater area. Shape is identical, even the probable energies will be same, but the only difference is the total area, higher concentration, large area. So the particles which have energy more than activation, large area is having energy more than activation. This will result in a faster rate of the reaction and leads to greater, if it depends on how you change the concentration, either by changing the volume or you keep the volume same and add more particles. Both affects the concentration, and increasing the concentration increases the rate of the reaction. Is it clear, this idea of how the concentration affects the rate of the reaction and what will be the change in the shape of the graph as the concentration changes? So at higher concentration, there are more particles per unit volume. So the particles collide with a greater frequency, number of collisions basically, that will leads to faster or a greater rate of reaction. Is it clear, this part? So the change in concentration also, there are two ways the concentration can affect the rate of the reaction. It will affect the rate of the reaction, but the final product, whether it will affect the final product or no, that depends on which concentration is being changed. Like if you are changing a limiting or excess reagent. So if we change the concentration of a limiting reagent, so if we change the concentration or amount of limiting reagent, what will happen? Both the rate and amount of product will change. But if we change an excess reagent, then the rate will change, but the product, the amount of product remain unchanged. So example, if the reaction is there between zinc and hydrochloric acid, and we are using excess, this will result in a formation of zinc chloride plus hydrogen gas. And we are using an excess of zinc, more than enough zinc, and hydrochloric acid is a limiting. What it will do, it will result in a formation of salt and hydrogen, and we are collecting a hydrogen gas. That is example, we collect the volume of the hydrogen gas with respect to time. This is the shape of the graph. Now, if for example, as HCl is a limiting reagent, first I was using example 1 mole per dm cube. Now what I did, I'm using 2 mole per dm cube, I'm using a greater concentration of HCl. So if increase the concentration of limiting reagent, it, because 1 mole will produce 1 mole per dm cube of HCl produce different amount of hydrogen compared to 2 moles per dm cube. So what it result? It will result in a faster rate as well as different amount. So this is for 2 mole per dm cube, and the first one is for 1 mole per dm cube. If we change an access reagent, the limiting which we are using in access, like example, both example, I was using 4 grams of HCl and this 4 gram was enough, more than enough for a complete reaction. Still it is left. But if we change the access reagent, like I took 1 mole per dm cube of HCl, now I'm using say 8 grams of zinc. So what happened again, because the amount of the product depends on the limiting reagent, as a limiting reagent does not change, so amount of hydrogen will be same. The only thing, because greater number of the particle of zinc, so what it shows, it will show that then the particle will collide with each other and this will result in a formation of a product. So but the amount of the product will not change. Only thing what it affects, the volume of the hydrogen, the gas given off with respect to time. So steeper, quickly it will react, but the final amount will be same. So you have to read the question properly when you are sketching a graph related to the rate or the speed of the reaction, whether the limiting reagent is changed or access reagent is changed. So when we increase the temperature, as you can see here clearly, that the shape of the graph will change, the height of the peak will decrease and it will shift towards right hand side. So greater number of the particles will have energy more than activation energy, which result in a faster rate of the reaction. Increasing a surface area, large surface area, small particle size, they will have more collagen, which result in a faster rate of the reaction. But you cannot use a Maxwell-Boltzmann distribution graph to show the effect of surface area. We can use the temperature, we can show the effect of temperature, like how the shape of the graph will change if we change the temperature, if we change the concentration, but we cannot draw a graph for surface area, as this one is not showing any effect or anything related to surface area. If we use a catalyst, what is the effect of the catalyst? Catalyst lower the activation energy. So example, if uncatalyzed reaction, this was the activation energy. But when we use a catalyst, what catalyst will do, they will alter the activation energy, providing an alternative route or path for the chemical reaction. So with the catalyst, you can see greater proportion of the particle will have energy more than activation, as catalyst is not changing the shape of the graph. Only thing what they change is the activation energy. They lower the activation energy so that greater number of the particles will have energy more than activation, leads to a greater rate of the reaction. The catalysts are of two types. One is called homogeneous catalyst, another one is heterogeneous. Normally we use heterogeneous catalyst. The term hetero means that the phase of the catalyst and the phase of the reactant is different. We call that as heterogeneous. Like example, when we manufacture ammonia by a Haber's process, nitrogen and hydrogen are in a gaseous state. But what we use as a catalyst, we use iron as a catalyst. So iron is a solid state. Reactant are in a gaseous state and catalyst which we are using in a solid state. So when we are using different states, we call this catalyst as heterogeneous. Like state of the catalyst is different from state of the reactants. A homogeneous catalyst where the reactants as well as the catalyst having a same phase, and that you will study in detail in A2 unit 5. The reaction, the reversible reaction, the reactants in reversible reaction, the reactant can form a product and the product can decompose and form back the reactant. So this type of reaction is known as the reversible reaction. And for reversible reaction, we define a term equilibrium, the term equilibrium means when the rate of the forward reaction and the rate of the backward reaction is same and there is no change in concentration. Like example, if you was having say 2 mole per dm cube or 2 grams of the reactant and you have 5 grams of a product, once a reactant form a product, if 1 gram of a reactant is forming a product at the same time, 1 gram of a product decompose and form back the reactant. So the concentration overall, there is no change in concentration, and we call this as equilibrium or dynamic equilibrium. And this equilibrium is affected by the change in concentration, by changing the pressure, and by changing the temperature. For temperature, it depends on which reaction, whether the forward reaction is endothermic or exothermic. So example, we have a reaction which is reversible as well as the forward reaction is endo. Because we write a reactant and product according to forward reaction. So if the reaction is endothermic, the reactants will have low energy and the product is having high energy. Whereas if the forward reaction is exo, reactants will have high energy and the product will have low energy. On y-axis we have energy, and on x-axis reaction progress. Now what happened? First, in a reversible reaction, reactant gain energy, and if the reaction is endothermic, reactants absorb energy, greater amount of energy they absorb. Minimum possible energy at which the reaction start, we call that as activation energy. Once they reach the activation energy, they will form a product. They release some of the energy, but energy which is taken in is more than energy given out. That's why the overall reaction is endo. The minimum possible energy at which this reaction is starting, that's called activation energy. Now, what is the effect of temperature on endothermic reaction? Because if I increase the temperature, so if we increase the temperature, what happens? We have both reactant and product, but reactants have low energy and the product is having high energy. So energy is absorbed by most of the reactant. As a result, they will form greater amount of product. So increase in temperature will shift the equilibrium or the balance towards right hand side. And if we remove energy, we have both reactant and product, but product is having greater energy, so most of the energy is lost by the product. As a result, it will form back the reactant. So decrease in the temperature or removing the heat energy will shift the equilibrium towards left hand side. If equilibrium shift towards right hand side, the yield increase, you will get more product. Equilibrium shifted towards left hand side, the yield will decrease and the amount of product will also decrease. For reversible reaction, which is exothermic, reactants have more energy, product is having less energy, they reach activation energy and form a product. But if I increase the temperature, I have both reactant and product, but because the product is having low energy as compared to reactant, so most of the energy is absorbed by the reactant, most of the energy absorbed by the product to form the reactant, so equilibrium will shift towards left hand side. And if we decrease temperature, reduce the energy, the reactants have greater amount of energy, so reactant lose most of their energy. As a result, they will form a product. So for a reversible reaction, it depends on whether the forward reaction is exo or endo. As you can see, formation of ammonia by a Haber process, the forward reaction is exo. So if the temperature increase, the equilibrium will shift to oppose the change and move in endothermic or backward direction to try to decrease the temperature, and the position of equilibrium will shift towards left hand side, which lower the yield or decrease the yield. So you have to check first whether the forward reaction is endothermic or exothermic. The effect of pressure: when we increase the pressure, basically we reduce the volume or increase the concentration. So equilibrium always shifted towards side where number of moles are less. If we have equal number of moles, and this is valid for gases, so if we have equal number of moles, then there is no effect of pressure. If we have different number of moles, like here we have 3 moles and 1 mole, so when we increase the pressure, shift the equilibrium towards side where number of moles are less. So 3 moles in the reactant and 1 moles in a product. When we increase the pressure, we reduce the volume or increase the concentration, more the collision of the reactant molecule result here, shifting the equilibrium on the right hand side. But what is the effect? If we increase the pressure, we may get a higher yield, like more product. The reaction will be faster as well. But industrially, high pressure are expensive to produce because it increases the cost to pump the gases, as well as equipment is expensive to contain high pressure. That's why practically, like, we take a normal pressure for until unless it's not affected by other condition. And the reason is that the constraint is that because increasing the pressure will make the process expensive, as well as it required equipment which can withstand or hold or contain this very high pressure mixture or the reactants. Then what is the effect of concentration? Increasing a concentration, if we add reactant or we remove product, so if we add reactant or remove product, equilibrium will shift towards right hand side. And opposite will happen if we add product or remove reactant. The equilibrium shifted towards left hand side. So this is how the concentration affects. That's why to continuously collect a product, we are removing the product from the mixture so that the reaction favors the forward direction, and continuously we'll get the product. So example, iodine is there and hydroxide molecule in a reversible reaction. This is iodine, which is colorless. Water is there and iodide ion. Now, if we increase the concentration of OH, if we add more OH, the equilibrium try to oppose this change, and where it will shift towards right hand side. So as it will shift towards right hand side, the color will get paler or lighter. Why? It's not like the total thing will turn into colorless, because when a reversible reaction is there, you have reactant and product both. Concentration changes, amount changes. So in this case, if we add an alkali or hydroxide, equilibrium shifted towards right hand side, which leads to a color change, or a color will become paler or lighter. And if we add acid here, if we add acid are proton donors. This H will react with OH, and what it will form? It will form H2O. So when it will form H2O, amount of water increases. What it result? It will result in a formation of more iodine molecules. Shift the equilibrium. In the left hand side, give a solution a dark color or a brown color. Catalyst is not having any effect on the position of equilibrium. The catalyst only affects the rate of the reaction, and it affects both rates, forward and backward. Both rates are affected by the catalyst. So industrially, for manufacture ammonia by a Haber's process, and manufacturing sulfuric acid, by a contact process. The second step, conversion of sulfur dioxide into sulfur trioxide. What it need or what it required a catalyst, which is vanadium pentoxide. So what is the effect of the catalyst? Catalyst does not change the equilibrium, but it increases the rate of the reaction. The reaction will occur at a faster rate. So a Haber process around 450 degrees centigrade, 200 to 1000 at ATM, and a catalyst iron is used. So lower temperature gives good yield but slow rate. And how we increase this rate? By using a catalyst. High pressure give a good yield and higher rate, and too high pressure would lead to too high energy cost and increases the cost. So to increase the rate, we use a catalyst here. Same thing for manufacture of sulfur trioxide from sulfur dioxide, as the reaction is reversible. So low temperature will give a good yield because the forward reaction is exo, but it will be a slow rate. So moderate temperature is used around 450. High pressure, because here we have one and a half mole, 1.5, and here we have 1 mole. Equilibrium shifted towards right. So high pressure give a slightly better yield and high rate too. So too high pressure will lead to a high energy cost and increases the cost for manufacture of that specific chemical. These are some more examples related to equilibrium, like practical production of methanol or hydration of ethene. What are the conditions? What catalyst we use? The forward reaction is exo. We use about 450 here. The forward is also exo. We use about 300 degrees centigrade. When you check the number of the moles, 2 moles, 1, so high pressure. When you check the number of moles, 3 mole and 1, so high pressure. And we use catalyst, chromium and zinc oxide. Here we use phosphoric acid as a catalyst. So this was the topic related to rate of the reaction, which is called reaction kinetics. In this rate topic, you have to the new thing which you studied today was the Maxwell-Boltzmann energy distribution graph. The reversible reaction is same as you already studied this reversible reaction. Is it clear? Any question related to the class? I'll share another link and discuss doubts related to the January 2018 paper.